Today we are going to talk about motors and gearboxes, and we will post all of these lessons on the wiki. Motors and servos, which we'll cover also. Servos are like motors, but they're really weak. We'll cover the motors and servos today. The other power sources we have in first are pneumatics, we have springs, and we have changes in center of gravity of the robot. That's another lesson. Couple things. First, motors are the way you turn electrical power into mechanical power in first. And you do it directly. Another important thing is with motors in first is that they're prescribed. There's a list you see on the right-hand side, that's Rule 32, Robot Rule 32, and it lists the motors that you can use. You can't use a motor if it's not on the list, and that's just the rules. Fortunately, there are a lot of motors on the list, and they include some really powerful ones. Before we go into the motors that we have, the way that you can tell, the performance of a motor is that every motor has a performance curve. They all look like this. They've got torque at the bottom, which is the force that you're putting out. And on the sides, they have speed, which is the blue line. At low torque, it's very high, decreases linearly to zero at maximum torque. You've got power, current rather, which is the purple line. It starts at zero, or close to zero at the minimum, at zero torque, and it increases the more torque, the more current you're drawing through your motor. Power is the red line. It's bell-shaped, and you have your maximum power at half of your stall torque. And the other line, green line's efficiency, how efficiently you're turning electrical power, watts of power into watts of mechanical energy. The key real parameters are here. You've got a speed at free speed. If there's zero torque, if your motor is just plugged in, turning, and you have no resistance, that's the free speed. That's at the blue line at zero torque. You also have the current at zero torque, because you still draw some current even if there's no resistance. So current at zero torque is where that purple line ends up hitting the axis. On the other two, you have two numbers at stall torque. You've got a current at stall torque, and you've got a, that's really it, you've got the stall torque. The motors that we have fall into two classes. We have, most of the motors that we can choose from are air-cooled. They have holes in the side, they have a fan built into them, and when you run that motor, that fan pulls air through the holes, runs it through the motor, cools it, and then out through other holes. Air-cooled motors use first force circulation through the motor to provide cooling. They've got the holes, they've got a fan. You can see all of those things when you look at the motor. They allow for very high power to weight ratios because they're well cooled. But if you stop them and you have current going to them again, if you're driving them and you stop them, stall them, you will burn them out really, really, really quickly. And then you'll see blue smoke come out. The other motors we have are sealed motors. Generally, those have bearings. They tend to be a bit better built, but they're heavier, a lot heavier. But they have the advantage that you can run them stalled. that you can put current on them and have them not move, and they're not going to burn out. They're much harder to destroy. In fact, some of them, are basically indestructible from a first standpoint. That's a wild statement to make, but it's true. There are also times when you want to actually hold the motor steady without turning under load. And we've done that a couple of times. In 2014, we had a catapult, and we pulled that catapult back until we had a 100-pound force on it. And then we held it there with that 100-pound force by just having the motor stand still. And we had PID control that said you move the motor to maintain that 100-pound force. We kept power on that motor the whole match, except for when it was fired, and it was fine. We did that the next year with the 2015 game, Recycle Rush, because we used it to lift stacks of totes. We were picking up 6 totes, a garbage can on top of that, and a pool noodle in that. The total weight of those game pieces that we were stacking ended up being like 66 pounds. And we would be holding that in place with 2 motors, one on the left, one on the right. We were coordinating those motors, but we were also basically having them provide the power to hold that stack in position without moving. Those were all done with sealed motors so that we were able to run those without them burning out. These are a bunch of useful motors that we have with FRC. So, top motor. One of our most powerful motors, called a sim motor. It's really, really heavy. It's 2.8 pounds. It is virtually indestructible. It is almost our most powerful motor. And it's really, we almost always use them for the drivetrain. We can use them for other things also. The second motor on the list is actually our most powerful motor, but it's air-cooled. It is this much more powerful than that motor. It's much, much lighter. It's 0.8 pounds instead of 2.8 pounds. But actually, that is our most powerful motor available in First right now. Really useful, but while it's really powerful, if you stall it, if you put it in a position where it wants to run and you stop it, you have probably a second or 2 before you let the blue smoke out. And then it doesn't work anymore. This is called a mini sim. It's exactly like a sim motor, but it's sawed off. And it is about 2/3 the power. It's about 2/3 the weight. It's a bolt compatible with a sim, so if you have a sim on your robot and you're sitting there and saying, oh my God, I need to lose a little weight on this robot, it's a little bit avoirdupois, how do I take some weight off? You could put mini sims on if they're powerful enough. And it's really easy change to make because it's just bolt compatible. You take off the sim, you put on the mini sim. We've done that. Bag motors look like sims. They're not. They're sealed. They're going to resist burning out pretty well. And they have the exact same power as this motor. We use this motor a lot. This is the Mark 9015 motor. This year we use this for the steering in our Swerve. So we've got 4 of these on our robot. That and the bag motor have the same power output. And on the side, we've got pictures of some of these motors that have gearboxes attached to them, because usually when we use a motor, we don't just use the motor, we have to use the gearbox too. So, we've got all these motors. How do you pick the right one? What do you do? What's the method here? And you really need to know, before you pick a motor, what do you need that motor to do? What's the job? How much force does that motor need to apply to whatever mechanism it applies that force to? How rapidly do you need it to move in terms of revolutions per second? If it's used for your drivetrain, ultimately that's going to determine what speed your robot's going to move. How quickly does it need to accelerate? Do I need to go from 0 to 10 feet per second in 1 second time? I don't know, but you need to know because you're designing the robot. What's the likelihood of stalling the motor? Because if it's an air-cooled motor and you stall it, you're going to have to change your motor, and you're not going to have that motor for the rest of your match. If you stall an air-cooled motor, you will burn it out. Also, will you need to hold, as part of your design, do you need to use a motor to hold something in a stationary position? In which case, you can also rule out an air-cooled motor. You have to use a sealed motor. How much space and how much mass can you afford? First puts limits on robot weight, 120 pounds without the battery or bumpers. So everything when you design, there's compromises to be made. Sometimes you might use an air-cooled motor if something might possibly stall if something goes wrong, just because I have no way to afford the weight of putting a sim motor on this. I can use a sim, I can use the 775 Pro. They're both basically the same amount of power. How do I choose? Maybe I need to use the 775 Pro, even if it might stall, because I can't afford the weight. I got a case study, picking a motor. This is a case study in recent history because it's our 2017 rope climb. We've got a 150-pound robot. We need to climb 36 inches. We need to do it in 10 seconds. And we're working against a gravitational force, and gravitational force is an acceleration. So the basic equations are there. The force that I need to apply is equal to the mass of the robot times the gravitational acceleration plus your desired acceleration divided by a constant. G sub c is a constant. All G sub c does is it allows, in English units, we use pounds for two things. We use pounds for force, we use pounds for mass. We pretend that they're the same thing. They're not. G sub c makes that conversion so that we're consistent in our units. G is 32 feet per second. G sub c is 32 also, and it has the right units so that when you throw it in there, if you need force to be your answer, force is the answer you get. If you're doing these calculations in metric units, you will not, the G sub c is not there because the units are already consistent. You're not using the same units for mass and force, but English does. So your acceleration, dv dt, is equal to force over mass times the gravitational constant, minus the gravitational acceleration. The drive force that you need to apply at the wheel, the F sub D, is the torque available at the wheel axle divided by the radius of the wheel. What's the working radius? Where is that actually going to be? So for the rope climbing, how big a coil are you going to make when you coil this rope to pull the robot up the rope? The radius of that coil is R sub W, so radius to center line of rope. A note, if the rope coils over itself, R sub W gets bigger if it wraps around itself, and you'll see that you need more torque to climb. If that happens, your motor starts working harder. Maximum velocity is based on geared rotation with the speed under robot weight. So we go to our motor performance curve, and one thing we don't want to do is we don't want to design our robot to be working on the low power side, on the high torque side, because you're working under conditions whereas when your torque increases, my available power drops. It's not a winning proposition. So you really want to be above the halfway point. Ideally, you want to design so you're running your motor between maximum power and maximum efficiency. The other thing is you need to look at your current, because where I drew this line, if I won't say I'm going to run over here, I want to run at maximum power, well, that means I'm running at 68 amps of current, and I've got a 40 amp breaker. Guess what's going to happen to that breaker? And blowing a breaker during a robot match is never a good way to win. So if I look at the curves, I come to some conclusions here. The sim curve indicates that at 40 amps, I only have around 0.5 foot-pounds of torque, although I've got a lot of revolutionary speed. I've got 63.2 revs per second. I certainly don't need that for climbing rope. On the other hand, if I've got a 1.5-inch rope diameter, so 0.75 inch rope radius, with a 150-pound robot climbing at a constant velocity, not even including acceleration, getting it up to speed, but just climbing at a constant velocity, requires a torque of about 9.4 foot-pounds. And going back to the performance curve, there's no 9.4 foot-pounds there. It just doesn't exist. So we need at least an 18.4 leverage to make that solution work. I can't spec a motor and just have a motor driving that. There's no motor available in first that will do that job. What is torque? Because we're talking about torque a lot here. Torque is basically rotational force. We normally talk about using it in foot-pounds, which is the typical English American way of representing it. If you're not using American units, it's in Newton meters. Sometimes we put ounce, inches. It's important to remember that if we're using those American terms, that the foot-pounds, the pounds are pounds of force, not pounds of mass. The ounces are ounces of force, not ounces of mass. And the reason you use ounce inches is because they make little numbers of torque look bigger. If you have a wheel and you have a certain amount of torque that's being applied, you've got a radius on the wheel, your actual drive force is going to be the torque divided by the radius. So we have a conundrum. For the most part, motors are not directly useful. They rotate too fast. They don't provide the torque we need. Is there only some way to leverage that excess speed to create more torque? And Shazam, gearing provides rotational leverage, trading off speed for torque. And the trick here is not all gearing uses gears. You can use chains and sprockets, belts and pulleys. You can also change your work radius. So if I change the work radius of that lift to almost 0, I might solve the torque problem. But it's not a really good solution. By the way, changing the work radius is why old bicycles look like that. They were too easy to pedal because they were old pedaling, did not have gearing. You pedaled the wheel directly. And it was too easy to pedal and too slow when the wheel was just like a normal bicycle wheel. So they made the wheels bigger. Go back to the motor performance curve now that we know that we can use gearing, and I've got a couple of solutions. One of them is just about at the maximum efficiency, and that uses about a 48-to-1 reduction. And there's a reason why we have two of them up here. When we first built the robot, we started with a 48-to-1 reduction. It was very efficient. And then we changed it to a more aggressive 25-to-1 reduction because we wanted to climb faster. Based on the curves, 48-to-1, the motor was putting out 1.96 foot-pounds torque at 79 revs per second. It was drawing about 14 amps. That provided us, after the gearing, with 9.4 foot-pounds of torque available with a 1.65 rev per second climb at the climber. And that meant that we were climbing potentially at 7.8 inches per second. I could do the 36 inches in about 4.6 seconds. When we changed that to the gearing, the 25.2-to-1, we increased that speed to 13.1 inches per second, getting the climb time down to a bit under 3 seconds for just the actual climbing. But we also were pulling 30 amps at that higher speed. The motor we picked to do this was the sim motor. We needed a powerful motor to lift. We basically had a choice between using a sim and using a 775. By using the sim, we didn't worry. If we needed to hold it up without moving the motor, we could do that without burning it out. We get worried about stalling that 775, so we used a sim, and that worked pretty well. Gear types. Any questions so far? The gearing we used for the climbing, rope climbing, are spur gears. Spur gears are just regular gears. They mesh with each other at the edge. It's what you think about when you think about gears. For each stage of reduction, the reduction is the driven gear tooth count divided by the drive gear tooth count. The drive gear tooth count is the one that your motor is turning. The driven gear is the one that it turns. And for multiple stages, because this is a 3-stage reduction, you multiply the reduction for each stage. So if you had 3 stages at 3-to-1 reduction, 3 times 3 is 9, times 3 is 27-to-1 reduction overall. We use Planetary gears a lot. In Planetary gears, you have your gears inside a tube, which has gears on the inside of the tube. Each stage has a sun gear. The sun gear is attached to a gear holder, planet holder, and then you have planets. So you've got the sun gear moving in the middle. You have planets which connect the sun gear to the inside teeth, and they all spin together. The reduction is the ring gear tooth count, that those teeth on the inside of that tube. How many teeth does that have? Divided by the sun gear tooth count, and then you add 1, plus 1. And again, for multiple stages, you multiply the reduction. We actually have 7 of these on Dubot 13. So we use that a lot. We have 2 spur gear systems and 7 planetary systems. And then worm gears, usually it's only 1 stage, but you can have really, really large reductions on worm gears. The reduction is worm gear tooth count divided by the worm stud count. And depending on the angle of the worm gears can be designed so that they don't back drive. So if you were using this to climb a rope, for example, and you turned off power at the end, your robot would not slide down. We didn't use that, but we could have. It was an option. There are also shifting gearboxes. You can have gear shifts. Usually it's just 2 gear ratios that you have a choice between. You could have 1 for high speed, 1 for power and fine control. They're used on drivetrains a lot, where I want to be able to drive fast, but I need to be able to control the robot at low speed to do fine maneuvering, say putting a gear on a peg. These are available from a number of suppliers. They can be have 1 to 3 sims mounted on each one, so they can be very powerful. They're normally used with tank drive, and with tank drive they almost always have 2 or 3 sims. Use pneumatic control for shifting, and there are 2 types of shifting mechanisms, which I won't get into here. One's called a dog gear, and one's called a ball locking shifting. We did use gear shifting robots in 2 of our old robots, Dubots 3 and 4, but we haven't used them very much. Versa Planetary is a planetary gear system we use a lot. Vexpro developed a very flexible modular planetary gear system. It's very flexible in terms of what motors you can put on it. You can even put sims on this thing. It includes a lot of mounting hardware for different motors when you buy it. So when you buy it, you have a choice of mounting the 775 Pro or a bag motor or that little Landymark motor. It's all really easy to do. You have to buy an extra piece if you want to put a sim on it, but that extra piece is not a big deal. You can buy a dual motor mount. And in fact, we designed a triple motor mount for the shooter this year. We're putting 3 of the most powerful motors available on the shooter. it's almost necessary for using the 775 Pro and most powerful motor. It's really hard to mount that any other way other than using a Planetary. And with a Planetary, it's really, really easy. You have a choice. At each stage, you can have a 3, 4, 5, 7, 9, or 10 to 1 reduction. And it's designed so that it can be used for 0, 1, or 2 stages, but we've made 3-stage versions and all you need to do for the 3-stage is buy another stage and buy longer bolts to hold it all together. It's heavier and more expensive than the Bainbot Planetary gearboxes we use, but it's also a bit more robust and flexible. We also use Bainbot Planetary system. It's designed for Bainbot motors, but we can use the Andy marks on them. We can't use Sims, we can't use mini Sims, we can't use bag motors. They are compact and lightweight. They're not cheap, but they're cheaper than the Planetary. And each stage can be 3, 4, or 5 to 1 reduction. It's available in 1 to 4 stages. You need to know that when you buy it because you're going to buy the actual gear reduction you want. But you can go anywhere from a 3 to 1 reduction to a 672 to 1 reduction, which is crazy. We have a lot of these gearboxes. We have like boxes of them because we buy them. We buy at least 8 of these every year. And the reason we buy 8 of them every year is that our swerve module uses one of these for steering. We use the 3-stage 132 to 1 reduction gearbox, and we never reuse those for the next year's swerve because they're worn, and we always put a new one, so we have a lot. We have used old ones for other purposes, not for steering. We have used old ones for prototyping as well, and certainly you can buy spare parts so that you can rebuild these if you want. We just don't so much bother. They're torque limited compared to Planetary because their gears are sintered metal, basically metal forced together at high pressure and temperatures, but if you apply too much force to these gearboxes, you'll turn the gears into dust and it doesn't work so well. We generally are using less of these over time. We're using more Planetaries, less of the P60s, but we still use the P60s because light and cheap is sometimes good. By the way, cheap means like $50 or $60 for a gearbox. It's not $10. Where do we buy these? A few places. Andy Mark is a good source for a lot of gearboxes. They've got spur gearboxes. They've got Planetary gearboxes. They have bevel and worm gearboxes. They have shifting gearboxes. Andy Mark is also a good place for buying gears. If you're going to design a gearbox, you need a gear, you can buy them from Andy Mark. You can get motors there, and Andy Mark is unique because it stocks parts for both FRC and FTC. So it's friendly to both of those systems. Another really good place to buy parts, and we probably split our business about equally between those two, the first two. Vex Robotics has a Vex Pro series. They've got really well-designed set of gearboxes available, including the West Coast drive gearboxes. They got spur gears. They've got 1 and 2 speeds, the shifting gearboxes. They've got the Planetary system. They have an absolutely awesome supply of spur gears. If you want to design your own gearbox, man, they have everything. And
not only do they have everything, but the gears are made out of 7075 aluminum, so they don't weigh, a huge amount. They've got motors, they've got Sims, mini Sims, bags, and they have the 775 Pros. So they get a lot of our business as well. Drawback is they're in Texas, and it takes longer to get stuff from them. Bainbots, Planetary gears, and they have small motors. If you're designing with gears, and we did this for the climbing gearbox. That was a homegrown gearbox that we put together. When purchasing gears that have to mesh, the gears need to all share the same diametrical pitch. The diametrical pitch is for 1 inch diameter gear. How many teeth does that have? If it's got, typically we're using 20 dp, so a 1 inch gear would have 20 teeth, a 2 inch gear would have 40 teeth, a 3 inch gear would have 60 teeth. And also the same pressure angle. Now fortunately they're all designed, you buy them from Vexpro or AndyMark, they tend to be all of the same diametrical pitch and contact angle, pressure angle. The other thing, if you're designing a gearbox, is that the center-to-center distances where the axles are, they need to be really accurate. Otherwise, the gearbox doesn't work. When we built our first gearbox, we did it on drill presses, and it was really a very painful effort. We remade those plates 3 times before we got it good enough so that it actually worked. And now servos. Any questions about motors? Any questions about gearboxes? Yes?
What do you mean by this stage of the gearbox?
If I got spur gears, and I have one gear which drives another gear, that's a stage. If I want to have a second stage, so this has an axle on it, I would put another gear on that same axle so that this gear drives the little gear, and I would have it driving second. So these gears are stage 1. These gears are stage 2. If you want to have a third stage, you have another axle with another second gear on it, and it would be the third stage. With planetary gears, you got a planet carrier. It's got a number of planet gears. And there's a sun gear in the middle. This sun gear actually belongs to the stage above it. There's a sun gear down below. So, but each set of planets and suns is a stage. And each stage consists of a sun gear, a few planet gears, three or four typically, sometimes 5 planets, and a carrier, and that's a stage. And so this is, if this were 3 to 1, if this were 10 teeth and this is 30 teeth, and this is 10 teeth and 30 teeth, this is 3 to 1 and 3 to 1. So you have 9 to 1 total.
So then for planetary, it would multiply like that? Right?
Yeah, for planetary it does also. For each stage, let's say if you had this stage and it's 3 to 1,
and I've got another stage, also 3-to-1. It would be the same thing. And typically, our Planetary gearboxes, we use anywhere from 1 to 4 stages, but mostly 1 to 3. The shooter is 1 stage. It has a 3-to-1 reduction. That's it. Because we want the shooter to run really, really fast. And the way we get more torque, more power into the shooter is we put a lot more motors on. The climber climbs slowly. It isn't spinning, nothing's spinning as fast as the shooter on the climber. So there we have about a 25-to-1 reduction. And that's done in 3 stages. The steering gearboxes are 3 stages, and we have 130-to-1, because at that speed, your steering speed gets down to around 2 rotations a second. I could have the steering motor turn the pivot entirely around 2 times per second if I wanted to. And it turns out that that's a good speed for controlling the steering. And if I go much faster than that, then I have issues with just control response time. If I go slower than that, it's slow in response. So the only ones that we typically don't have multi-stage would be a worm gear. This is just, first, you don't much need it with a worm gear. It is capable of very high reductions. You could have a 50-to-1 in 1 stage in a worm gear. It would not be hard to design that. But also, it gets awkward. One thing about a worm gear is you've got a 90-degree change in orientation. Everything else, I've got the motor, I've got an axle, I have no changes in rotation axis. Everything's parallel. In a Planetary gearbox, the axis is all along the axis of the motor. In a spur gearbox, it's not. But all of the axles are still parallel. In a worm gearbox, I've got the motor here, I've got the motor axle, and here's my output axle. It's at 90 degrees. If I put more stages on it, I end up with additional 90-degree turns. It gets very awkward. So it's not that you couldn't, it's just you really don't need to and you really don't want to. If you need to use worm gears in multi-stages, you generally figure some other way to do that. Handymark has actually 1 gearbox where they combine spur gears with a worm gear. The first stage is a spur gear reduction. It drives the worm gear for the 2nd stage. Okay. Any other questions about gears or motors? So servos. Servos are very low power motors. They have gearboxes built into them. Mostly they're restricted motion. Some of them do continuous turning, but a lot of them turn either 90 or 180 degrees. And we haven't used a lot of servos until this year. And we did use some in Dubots 2 and 3 a long time ago. And we were really not happy with them. They got a reputation of being worthless and weak. And so we started using pneumatics to do their job instead of using servos. And that's where things stood until Dubot 13, where all of a sudden we had a lot of things to actuate. There are more moving parts on Dubot 13 than on any of our previous robots, and it's not even close. There's no contest. We have, first, more motors than we've had on any other robot up until now. We have 14 motors. And we've got 9 servos because we had more things to move. We use 4 for CVT shifting. We use 2 for gear release and capture. We use 2 to open and close that gear flap. And we use 1 for modifying the shooting angle. It's really a lot of uses. And they turned out to be very good for this robot. But when I talk about them being low power, they really are. And the key thing to look at here, so I've thrown the servos. This is the motors we talked about earlier. These are the servos we have available to us that we can buy. Now, the top 2 are actually pretty reasonable. This is the power, maximum power in watts. And with our motors, man, these 2, they're almost 350 watts. That's a lot of power. And 204, 180, 180, here's 250. My weakest motor is 11 watts. That's the FTC motor. We don't use that on our robot because it's, why would I use an 11-watt motor when I can use a 300-watt motor? Here, the servos, most of them are less than 1 watt of power. And when we did Dubots 2 and 3, all of the servos that we could buy were less than 1 watt of power. We used them for things like gear shifting, and you just didn't have enough power to shift a gearbox. If that gearbox were being used, if it were under load, the resistance against shifting gears was much higher than the servo could provide. But we do have a couple that are okay. The 4.5, that's that big honking servo that we use for the gears, and we also are using it for the angle adjustment. And it's really at 4.5 watts, it's not so bad. These are the smart servos that we're buying from Rev Robotics now. At 2.5 for a small servo, that's really good when you compare it to all of their brothers. They're light, they're about 1/10 of a pound, so weight is great, but you really need to understand that if you're working with servos, they can be very useful. They're certainly awesome for us this year. There's real power limits. So don't expect to move mountains with them. One thing though that's really important, and it's a feature we used in servos this year, it's like unlike the Matics are basically binary devices. I extend the cylinder, I retract it, and those are 2 states. I've got basically 2 states to work with, extended, retracted, that's it. Those are my choices. A lot of people work with servos that way too, and we sometimes do also. We did that with the gear collection and gear release. We did that with the flap, but with the CVT swerve, we're not doing that. We're actually controlling the position on where that arm is. And we're doing the same thing with the shooter angle adjustment. We're actually driving that to a specific angle so that we're shooting on the right trajectory. I can't do that with pneumatics. I can do that with servos, and that makes servos really useful. I could do that with a motor, but I would need to have an encoder, I would need to have feedback. Plus my motors are really powerful. I'm gonna break things. My original idea with controlling the shooting angle was to put a motor not a powerful motor, but a motor with a lot of reduction so that it was slow, but if that had reached its mechanical stop and not stopped, something would have broken. It would have had to, because even a weak motor with that reduction is gonna break something. Using the servo really saved us a lot in that. So it was the right place to use a servo and the right reason to use a servo. So that's it. That's the lesson. Any other questions?